Hey everyone, welcome back to the channel. Today we're diving into one of the most exciting frontiers in AI, multimodal NLP. Think about how humans understand the world. We don't just read text in isolation, we see images, hear sounds, watch videos, and combine all these sensory inputs to make sense of our environment. Now, AI is finally catching up. In this video, we'll explore how modern AI models like Clip, Flamingo, and Gemini are revolutionizing the way machines understand multiple types of data simultaneously. We'll look at real-world applications in search engines, media analysis, and content creation. We'll cover three main sections. First, what multimodal NLP actually is. Second, the groundbreaking models powering this revolution. And finally, practical applications that are changing industries right now. So, hit that like button, subscribe if you haven't already, and let's jump in. Let's start with the basics. What exactly is multimodal NLP? Traditional NLP, or natural language processing, focuses solely on text. It's amazing at tasks like translation, sentiment analysis, and text generation. But here's the thing, the real world isn't just text. Multimodal NLP takes this a step further. It combines natural language with other modalities. That's a fancy word for types of data, like images, audio, video, and even sensor data. The key innovation here is that these models don't just process each type of data separately. They create a shared understanding space where text, images, and other data types can interact and inform each other. For instance, imagine you show an AI a picture of a golden retriever playing in a park. A traditional image classifier might say, "Dog detected," but a multimodal model can understand the image and answer questions like, "What is the dog doing?" or "Describe this scene in a poetic way." The magic happens through something called joint embedding spaces. Think of it like a universal translator where different languages, text, images, audio are all mapped to the same conceptual space. This allows the model to find connections between a word like sunset and actual images of sunsets. Now, let's talk about the models that made this possible. First up, CLIP, which stands for Contrastive Language Image Pre-training, developed by OpenAI. CLIP was a game changer when it launched in 2021. Here's what makes it special. It was trained on 400 million image-text pairs from the internet. The training process is elegant. CLIP learns by looking at images and their associated text descriptions simultaneously. It uses contrastive learning, essentially teaching the model which text goes with which image, and equally important, which text does not go with which image. This creates two encoders, one for images and one for text, that map to the same embedding space. When the embeddings are similar, the image and text are related. When they're far apart, they're not. Let me show you how simple it is to use CLIP in practice. Here's a Python example, using the OpenAI CLIP library. We're loading an image and finding which text description matches it best among several options. Notice how we encode both the image and multiple text descriptions, then use cosine similarity to find the best match. The model returns probability scores for each description. The beauty of CLIP is its zero-shot capability. You can ask it to classify images into categories it was never explicitly trained on. If you want to detect cats wearing sunglasses, even though that wasn't a training category, CLIP can do it because it understands the concepts of cat, wearing, and sunglasses, and how they relate to visual features. Next up, let's talk about Flamingo, developed by DeepMind in 2022. If CLIP was impressive, Flamingo takes it to another level. Flamingo is what we call a visual language model, or VLM. It can handle interleaved sequences of images and text, meaning you can have a conversation that includes multiple images and it remembers the context. Here's what's incredible. You can show Flamingo a few examples of a task. We call this few-shot learning, and it can immediately apply that pattern to new examples. For instance, you could show it two images of different dog breeds with their names, then show it a third dog, and Flamingo will identify the breed. No fine-tuning required. The architecture is fascinating. Flamingo combines a frozen pre-trained vision encoder with a large language model. They're connected through special cross-attention layers that allow the language model to pull visual information when needed. This makes Flamingo incredibly versatile. It can do visual question answering, image captioning, visual reasoning, and even multi-image storytelling, where it creates narratives connecting several images together. Now let's talk about Google's Gemini, the newest and arguably most capable multimodal model in the game. Gemini comes in three sizes: Nano for on-device tasks, Pro for general use, and Ultra for the most complex tasks. What makes Gemini unique is that it was designed from the ground up to be natively multimodal. Unlike models that bolt together separate text and vision components, Gemini was trained from day one on text, images, audio, and video simultaneously. This native multimodality gives it deeper understanding. Gemini can understand and generate across all these modalities. It can analyze video content, understand audio and context, read handwritten notes, interpret charts and diagrams, and even understand code alongside visual outputs. In benchmarks, Gemini Ultra surpasses human expert performance on MMLU. That's a test covering 57 subjects, including math, physics, history, law, and medicine. It also achieves state-of-the-art results on 30 out of 32 benchmarks. Let me show you a code example of using Gemini's multimodal capabilities. Here we're using the Gemini API to analyze an image and answer questions about it. Notice how we can send both text prompts and images in the same request. The model returns detailed, contextual responses that demonstrate true understanding of the visual content, not just object detection. All right, so we've covered the technology. Now let's see how this is transforming real-world applications, starting with search. Remember when searching meant typing keywords and hoping for the best? Multimodal search changes everything. Take Google Lens. You can now point your camera at anything: a plant, a landmark, a product, an equation, and instantly get information. This is clip-like technology in action, matching visual inputs to text information. Or consider reverse image search. It's evolved from simple duplicate detection to understanding image content, finding similar styles, identifying objects, and even finding products from photos. The real breakthrough is multimodal queries. You can now search with a combination of text and images. For example, you could upload a photo of your living room and search "modern coffee table that would match this." The AI understands both the visual style and your text intent. YouTube search is becoming incredibly sophisticated. You can find specific moments in videos based on descriptions. Looking for the part where he explains the algorithm in an hour-long tutorial, multimodal models can identify that exact timestamp. In e-commerce, visual search is huge. Pinterest Lens lets you photograph anything and find where to buy it or similar products. Amazon uses multimodal understanding to improve product search and recommendations. Now let's look at how multimodal AI is revolutionizing media and content creation. First, content moderation. Platforms like Facebook, Instagram, and YouTube process billions of images and videos daily. Multimodal models can understand context. They can tell the difference between violence in news reporting versus violence being glorified. Automatic captioning has become remarkably accurate. YouTube's AI can now generate captions that understand context, slang, and even speaker diarization, knowing who's speaking when multiple people are in a video. Video summarization is another game changer. Multimodal models can watch an hour-long video and generate accurate summaries, identify key moments, and create chapter markers automatically. For accessibility, these models are life-changing. They can describe visual content for blind users with unprecedented detail and naturalness. They understand scenes, emotions, text and images, and context. On the creation side, we're seeing text-to-image generation with models like DALL-E, Midjourney, and Stable Diffusion. These are essentially multimodal models running in reverse, generating images from text descriptions. Here's a quick example of using a multimodal model for automatic video captioning. This code processes video frames and generates contextual descriptions. The model considers multiple frames to understand temporal context and generate coherent captions. For those interested in the technical details, let's dive a bit deeper into how these models actually work. Most modern multimodal models are built on transformer architectures. The key innovation is attention mechanisms that allow the model to focus on relevant parts of different inputs. Cross-attention is crucial. It allows the model to attend to visual features when processing text, and vice versa. Think of it as the model asking, which part of the image is relevant to this word? Or which words describe this visual region? Training happens in stages. First, encoders are pre-trained separately, image encoders on massive image datasets, text encoders on text corpora. Then comes alignment training, where they learn to map to a shared space. Contrastive learning is the secret sauce. The model learns by comparing positive pairs, matching images and captions, against negative pairs, non-matching combinations. This creates semantically meaningful embedding spaces. Both modalities need to be tokenized. Text becomes word or subword tokens, while images are split into patches that become visual tokens. Some models use 16 by 16 pixel patches, treating each as a token. There are different fusion strategies. Early fusion combines features early in processing, late fusion combines them near the output, and hybrid approaches use both. Each has trade-offs in computational cost and performance. Now, despite all this progress, multimodal AI isn't perfect. Let's talk about current challenges. First, computational cost. These models are massive. GPT-4 with Vision, Gemini Ultra, and similar models require enormous computing resources to train in one. This creates accessibility issues. Bias is a significant concern. Because these models train on internet data, they inherit societal biases. They might associate certain professions with specific genders or ethnicities, or generate stereotypical images. Hallucination remains a problem. Models sometimes confidently describe things that aren't in images, or make up facts. This is especially dangerous in applications like medical diagnosis or legal analysis. Fine-grained understanding is still difficult. While models can identify a dog breed, they might struggle with subtle distinctions or understanding complex spatial relationships and physics. Temporal understanding in videos is improving, but not perfect. Understanding long-term dependencies, tracking objects across scenes, or following complex narratives remains challenging. So, where is this technology heading? Let's explore the future of multimodal AI. First, embodied AI. Future models will integrate with robots and physical agents, allowing them to understand and interact with the 3D world. Imagine robots that can understand verbal instructions while processing visual and tactile feedback. Real-time processing is coming. As models become more efficient, we'll see live multimodal understanding in augmented reality glasses, enabling instant translation of signs, real-time scene descriptions, and contextual assistance. Beyond vision and language, we'll integrate more modalities: touch, smell, proprioception, and sensor data, truly universal models that understand the world like humans do through multiple senses and data types. Personalization will improve. Models will learn individual preferences while respecting privacy, becoming personal AI assistants that understand your context across all modalities. In science, multimodal AI will accelerate discovery, analyzing medical images with genetic data and patient histories, processing satellite imagery with climate models, or combining microscopy with chemical databases. Want to start building with multimodal AI? Here's how to get started. Several APIs are available. OpenAI provides GPT-4 Vision, Google has Gemini API, and Anthropic has Claude with Vision. Most offer free tiers for experimentation. For open source enthusiasts, check out Clip from OpenAI, LLAVA from researchers at University of Wisconsin, and Stable Diffusion for image generation. these can run locally with sufficient hardware. Great learning resources include the Hugging Face Multimodal course, papers with code for latest research, and YouTube channels covering AI developments. Here's a complete starter project using Clip for image search. This builds a simple image search engine. You can add images to a database, then search them using natural language queries. It demonstrates the power of multimodal embeddings for practical applications. And there you have it. We've covered the essentials of multimodal NLP, from the groundbreaking models like Clip, Flamingo, and Gemini, to real-world applications in search and media. The key takeaway? AI is moving beyond single-modality understanding to comprehend the world the way humans do, through multiple senses and data types simultaneously. This technology is still in its early days. As models become more capable, efficient, and accessible, we'll see innovations we can barely imagine today. If you enjoyed this deep dive, smash that like button and subscribe for more AI content. Drop a comment below telling me which multimodal application excites you most. Thanks for watching, and I'll see you in the next video. Keep exploring, keep learning, and stay curious about AI.